right, so let's start out with this somewhat corny and somewhat corporate, but still, I think, somewhat exciting video produced by a professional consultancy that uses R a lot in its work.
What's behind the statistics, the analytics, and the visualizations that today's brightest data scientists and business leaders rely on to make powerful decisions? You may not always see it, but it's there. It's called R, open source R, the statistical programming language that data experts the world over use for everything from mapping broad social and marketing trends online to developing the financial and climate models that help drive our economies and communities. But what exactly is R? And where did R start? Well, originally, R started here, with two professors who wanted a better statistical platform for their students. So they created one, modeled after the statistical language S. They, along with many others, kept working on and using R, creating new tools for R, and finding new applications for R every day. Thanks to this worldwide community effort, R kept growing, with thousands of user-created libraries built to enhance R functionality and crowdsourced quality validation and support from the most recognized industry leaders in every field that uses R, which is great because R is the best at what it does, letting experts quickly and easily interpret, interact with, and visualize data. Join the rapidly growing community of R users worldwide and see how open source R continues to shape the future of statistical analysis and data science.
Okay, great. So my own presentation will be a bit more sober, will not involve that much exciting background music. But as you saw in the video, R is sort of a general purpose programming language, but it was created mostly for statistical work. So it's designed for statistics, for data analysis, for data mining. And so you can see this in a lot of the design choices that the makers of R made. It's designed for largely people who are not experts in programming, who are just picking up programming on the side so they can do their work in social science or in statistics or whatever. It has a lot of very important differences from C, but the syntax and the paradigms that it uses are broadly the same, and you should feel pretty much at home right off the bat. It's an imperative language. Don't worry too much about that if you don't know the term, but there's a distinction between imperative, declarative, and functional. Imperative just means you make statements that are basically commands, and then the interpreter or the computer follows them one by one. It's weakly typed. There are no type declarations in R, and then the lines between different types are a bit more loose than they are in C, for example. And as I said, there are very extensive facilities for graphing, for statistical analysis, for data mining. These are both built into the language, and there are, as the video said, thousands of third-party libraries that you can download and use free of charge with very loose license conditions. So in general, I'd recommend that you look at these two books if you're going to work on R. One of them is the official R Beginner's Guide. It's maintained by the core developers of R. You can download it, again, free of charge and legally at that link there. All these slides are going to go up on the internet, on CS50's website after this is done, so no need to copy things down frantically. The other one is a textbook by Kozma Shalizi, who is a statistics professor at Carnegie Mellon, called Advanced Data Analysis from an Elementary Point of View. This is not principally an R book. It's a statistics book, and it's a data analysis book. But it's very accessible to people who have a modicum of statistics knowledge. I have never taken a formal course. I just know bits and pieces from various allied subjects that I've taken courses in, and I was able to understand it perfectly well. All of the figures are given in R. They're made in R, and they also have code listings below each figure that tell you how you make each figure with R code. And that's very useful if you're trying to emulate some figure you see in a book. And again, free download, stat.cmu.edu/cshalizi/ sorry, that should be /tilde/cshalizi. I will make sure to correct that when the official slides go up. /ADAFAEPOV, which is just the acronym of the book title. So general caveats, R has a lot of capabilities. I'm only going to be able to cover the surface of a lot of things. Also, the first portion of the seminar is going to be something of a data dump. I'm quite sorry about that. Basically, I'm going to introduce you to a lot of things right off the bat, going as quickly as possible, and then we can get to the fun part, which is the demo, where I can show you everything that we've talked about on the screen, and you can play around on your own. So there's going to be a lot of technical stuff thrown up on here. Don't worry about copying all of that down, because A, you can get all this stuff on the CS50 website later, and B, it's not really that important to memorize this from the slides. It's more important that you get some intuitive facility with it, and that comes from just playing around. So why use R? Basically, if you have a project that involves mining large data sets, data visualization, you should use R. If you're doing complicated statistical analyses that would be difficult to do in Excel, for example, it would also be good. Also, if you're doing statistical analysis that's automated. Let's say you're maintaining a website and you want to read the server log every day and compile some list of like the top countries that your users are coming from, some summary statistics on like how long this went on your website or whatever, and you want to run this every day. Now, if you're doing this in Excel, you'd have to go to your server log, import that into an Excel data spreadsheet, run all the analysis manually. With R, you can just write one script, schedule it to run every day from your operating system, and then every night at 2 a.m. or whenever you schedule it to run, it will look through your internet traffic for that day, and then by the next day, you'll have this shiny new report or whatever with all of the information you asked for. So basically, R is for statistical programming, for statistical analysis. Preliminary is done. Let's get into the real things. So there are three real types in the language. There's a numeric type. There's sort of a difference between integers and floating points, but not really. There's a character type, which is strings, and there's a logical type, which is booleans. And you can convert between types using these functions as numeric, as character, as logical. If you call, for example, as numeric on a string, it will try to read that string as a number, the same way that A2I and scanf do in C. If you call as numeric on true or false, it will convert it to 1 or 0. If you call as character on anything, it'll convert that into a string representation. And then there are vectors and matrices. So vectors are basically one-dimensional arrays. They're what we call arrays in C. Matrices, two-dimensional arrays, and higher dimensional arrays, you can have 3, 4, 5 dimensions or whatever. Of numeric values, of strings, of logical values. You also have lists, which are a kind of associative array. I'll get into that in a bit. So one important thing that trips people up in R is that there are no real pure atomic types. There's no actual distinction between a number, like a numeric value, and a list of numeric values. Numeric values are considered the same as vectors of length 1. And this has a number of important implications. One, it means that you can do things very easily that involve like adding a number to a vector. R will basically figure out what you mean by that, and I'll get to that in a second. It also means that there's no way for the type checker, to the extent that something like that exists in R, to tell when you've passed in a single value when it expects an array, or vice versa, and that can cause some odd troubles that I ran into when I was using R during my summer job. Right? And there are no mixed type arrays. So you can't have an array where the first element is, I don't know, the string John, and the second element is number 42. If you try to do that, then you'll get everything just converted to a string. So we have string John, string 42. So unusual syntactic features. Most of R's syntax is very similar to C. There are a few important differences. Typing is very weak, so there are no variable declarations. Assignment uses the strange arrow operator, less than, hyphen. Comments are with the hash mark. I guess nowadays we call it hashtag, though that's not really accurate. Not the double slash. Modular residues are with 2% signs. Integer division is with %/%, which is very hard to read when it's projected up on the screen. You can get ranges of integers with a colon, so 2:5 will give you a vector of all the numbers 2 through 5. Arrays are one-indexed, which screws a lot of people up if they're from more typical programming languages like C, where most things are zero-indexed. Again, this is where R's heritage as a language for not professional programmers comes in. If you're if you're a sociologist or an economist or something and you're trying to use R basically as an adjunct to your more important professional work, you're going to find 1 indexing a bit more natural because you start counting at 1 in everyday life, not 0. For loops, this is similar to the for each construct in PHP, which you'll get to learn in pretty soon, which is for value in vector, then you can do things with value.
That's come up in lecture.
Oh, that's come up in lecture. Oh, excellent.
The assignment, is it supposed to point from right to left?
From right to left, yes. You can think of it as the value on the right gets shoved into the variable on the left.
Okay.
And finally, function syntax is a bit strange. You have the function name foo assigned to this keyword function, followed by all the arguments, and then the body of the function after that. Again, these things may seem a bit strange. They'll become second nature after you work with the language for a bit. So vectors. The way you construct a vector is you type C, which is a keyword, then all the numbers you want, or strings, or whatever. Arguments can also be vectors, but the resulting array gets flattened. So you can't have arrays where some elements are single numbers and some elements are arrays themselves. So if you try to construct some array where the first element is 4 and the second element is the array 3, 5, you'll just get a 3 elements of array 4, 3, 5. They can't be of mixed type. If you try to read or write outside of the bounds of a vector, you'll get this value called NA, which stands for missing value. And this is what it's intended for, like statisticians who are working with incomplete data sets. If you apply a function that's supposed to take just one number to an array, then what you'll get is the function will map over the array. So if you have a function that, say, takes a number, returns its square, you apply that to the array 2, 3, 5. What you'll get is the array 4, 9, 25. And that's very useful because it means you don't have to write for loops for doing very simple things like applying a function to all members of a data set, which if you're working with large data sets, you have to do a lot. Binary functions are applied entry by entry. I'll get into that. You can access them with arrays or vectors with square brackets. So vector name square brackets 1 will give you the first element. Vector name square brackets 2 will give you the second element. You can pass in a vector of indices, and you'll get back out basically a subvector. So you can do vector name brackets C2, 4, and you'll get out a vector containing the second and fourth elements of the array. And if you want just a quick summary statistic of a vector, like interquartile range, median, maximum, whatever, you can just type summary, vector name, and get that out. That's not really useful in programming, but if you're playing around the data sets, it's handy. Matrices, basically higher dimensional arrays. They have this special initialization syntax matrix with an array that gets filled in, matrix with data, number of rows, number of columns. When you pass in data, it fills in the array, basically going top to bottom first, then left to right, so like that. And R has built-in matrix multiplication, spectral decomposition, diagonalization, a lot of things. If you want higher dimensional arrays, so with 3, 4, 5, or whatever dimensions, you can do that. The syntax is just array, dim equals C, then the list of the dimensions. So if you want a 4-dimensional array with dimensions 4, 7, 8, 9, the array dim equals C, 4, 7, 8, 9. And you access single values with brackets, first entry, comma, second entry. You can get entire slices of rows or columns. With this incomplete syntax, it's just row number, comma, or common column number. So lists are kind of associative array. They have their own syntax here. Again, don't frantically copy all of this down. This is just so that people going through the slides later have this all in a nice reference. And this will become very natural once I actually walk through the demos. So lists are basically associative arrays. You can access values with list name, $, key. So if your list is named foo, then you can access it like that. You can get an entire key value pair by passing in the square bracket index. If you read from a non-existent key, you'll get null. It won't error. The thing is, R will do as much with null as it can, and this can mean that if you're not expecting to get null out of some list read, you'll get some unpredictable errors further down the line. This happened to me in my summer job when I was using R, where I changed how a certain list was defined in one spot but didn't change later on the code that read values from it. And so what happened was I was reading null values out of this list, passing them into functions, and then being very confused when I got all sorts of random infinities cropping up in this function, because if you apply a certain maximum or minimum functions to null, you'll get infinite values out. Data frames, they're a subclass of list. Every value is a vector of the same length, and they're used for representing basically data tables. There's this initialization syntax. This will all, again, be much clearer when you get to the demo. And the nice thing about data frames is that you can give names to all the columns and names to all the rows. And so that makes accessing them a bit friendlier. Let's see. Also, this is how most functions that read in data from Excel spreadsheets or from text files, for example, will read in their data. They'll put it into some sort of data frame. So functions. The function syntax is a bit weird. Again, it's name of the function, assign this keyword function, then the list of arguments. So there's some nice things about how functions work here. For one, you can actually assign default values to certain arguments. So you can say arg1 equals, so you can say foo is a function where arg1 equals something by default if the user specifies no arguments. Otherwise, it's whatever he put in. And this is very handy because a lot of our functions have often dozens or hundreds of arguments. For example, the ones for plotting graphs or plotting scatter plots have arguments that control everything from the title and the axis labels to the color of regression lines. And so if you don't want to make people specify every single one of these hundreds of arguments controlling every single aspect of a plot or a regression or whatever, it's nice to have these default values. And then you can actually write, as you saw back here, or find a better example. Yeah, when you call functions, you can actually call them using the argument names. So here's an example of the matrix constructor. It takes 3 arguments usually. You have data, which is a vector. You have nrow, which is the number of rows. You have ncol, which is the number of columns. The thing is, if you type nrow equals whatever and ncol equals whatever when you're calling this function, you can actually reverse them. So you can put ncol first and nrow second, and it will make no difference. So that's a nice little feature. Data import and export, this can be done, basically. There are also facilities to write out arbitrary R objects to a binary file and then read them back in later, which is handy if you're doing a big interactive session in R and you need to save things very quickly. By default, R has a working directory that files get written out into and read back in from. You can see that with getwd, change it with setwd. Nothing especially interesting here. So now the actual statistics stuff. Multilinear regression. So the usual syntax is a bit complicated. It's model, or the model is a big object, basically. It gets assigned to lm, which is a function call. The first element, the y tilde x1 plus whatever. My syntax here is a bit confusing. I'm quite sorry. This is the standard way that computer science books do this, but it is a bit weird. So basically, it's lm parentheses. First item is variable, sorry, dependent variable tilde x1 plus x2 plus however many independent variables you have. And then these can either be vectors, all of the same length, or they can be column headers in a data frame that you can specify in the second argument data frame. And you don't have, and you can also specify more complex formulas, so you don't have to linearly regress a one dependent variable or one vector on a pre-existing vector. You can do, for example, a vector component y squared plus 1 and regress that against the log of some other vector. You can print summaries of the model with this command called summary, just summary parens model. Again, something else I should clarify, and with summary. Yeah, something else that will get corrected when the slides go up on the internet. If you just want to calculate a simple correlation, you can use correlation, vector1, vector2, this function core. Method is by default Pearson correlations. Those are the standard ones you can do. There are also Spearman and Kendall correlations, which are some variety of rank order correlation, where they don't calculate product moments between the vectors themselves, but of the vectors' rank orders. I'll explain that later.
Quick question.
Sure.
So when you're calculating for the simple correlations, do you assume that there's a statistical significance to the correlations?
You don't have to. Again, an LM is basically just a machine. It'll take in two things. It will spit out coefficients for the best fit line. It'll also report standard errors on those coefficients, and it will tell you, like, is the intercept statistically significant or different from 0? Is the slope of the best fit line statistically different from 0, etc. So it assumes nothing, I think, is the best answer to your question. OK, plotting. So the main reason you should use R, like multilinear regression, basically every language has some facility for that. And honestly, R's syntax for regression is a bit arcane. But plotting is where it really shines. The workhorse function is plot, and it takes two vectors, x and y. And then the ellipsis stands for a very large number of optional arguments that control everything from titles to colors of various lines or various points to the type of plot. You can have scatter plots or line plots. Pardon. Yeah. The arguments are two vectors of the same length. You can proceed this with attached data frame in your script, and this will let you just use column headers instead of separate vectors. And you can add best fit lines and local regression curves to your graph with these commands listed here, AB line and lines. By default, these get written into pop-up windows because it assumes that you're using R interactively. If you're not, you can write two files that are in really any format you'd like. Sorry. Another typo I just realized. Dev.off. Yeah. If you want to open another graphical device, you can use this function called PNG or JPEG or a lot of other image formats. And you can write graphs through whatever file name you specify. To cancel that, you have to use, I didn't write this in the slide, but there's a function called dev.off that takes no arguments. And then there are facilities for 3D plotting and for contour plotting if you want to make graphs of two independent variables. I won't get into these right now. There are also some facilities for animation, mostly maintained by third parties. I have done animations with R graphs, but I haven't used these third-party libraries, so I can't really attest to how good they are. What I recommend if you want to make animations using R is you can write out all of the frames for the animations, and then you can use a third-party program. Typical ones are called FFmpeg or ImageMagick to stitch all of your frames into one animation. So, time for a demo. So if you're using any Unix-like system, which is Linux, BSD, but who uses BSD? OS X, open a terminal window and type R at the command prompt. If you have RStudio or the like, that also works. For Windows users, you should be able to find R in your start menu. It should be called something like R, x64, 3 point whatever. Open that up there. So now, let me just open a terminal window. All right. Search. Command space, thank you. I do not ordinarily use Macs. Terminal, shell, new window with settings basic, R. So you should get a welcome message, something like this. So, I'm using R interactively. You can also write R scripts, of course. Basically, scripts run the exact same way as if you were sitting at the computer typing in every line one at a time. So let's start by making a vector. A, arrow, C, 1, 2. 1, 2, 4. OK, sure. Can we make the font size bigger? Command plus. All right. How's that? Good? OK. So let's start by declaring a vector. Let's do A, arrow, C, 1, 2, 4. We can see A. Don't worry about the bracket there. The bracket is also if you print out very long arrays, we can see like where you are. One example would be if I just type range 1 to, or I'll do that, something 2 to 200. If I print out a very long array, the brackets are just so I can keep track of which index we're on if I'm looking through this visually. So anyhow, we have A. So I said before that arrays interact very nicely with, for example, unary operations like this. So what do you think I'll get if I just type A plus 1? Yep. All right, now I'll make this different array. Let's say B, C, 20, 40, 80. So what do you think this command will do? Add the elements. So, and basically that's what it does. So this is pretty convenient. So how about I do this? C is, let's say, 6 times 1 to 10. So what elements does C contain, do you think? Yeah. So all the multiples of 6. Now, what do you think will happen if I do this? So I'll make this a bit clearer. C. So what happens do you think if I do this? A plus C. We're adding a 3-element array and a 10-element array.
Either an error or it just adds the first 3 elements.
Not quite. This is what we get. What happens is a shorter array, A, gets cycled. So we get 1, 2, 4, 1, 2, 4, 1, 2, 4. Yeah. And basically you can view this behavior before, A plus 1, as a subclass of this behavior where the shortest array is just the number 1, which is a 1-element array. I should be saying vector all the time instead of array because that's what the R documentation usually does. It's an ingrained C habit. OK. And so now we have this array. So we have this array C. We can get summary statistics on C, sum array C. And that's nice. So now let's do some matrix things. Let's say M is a matrix. Let's make it a 3 by 3 one. So n rows equals 3, n calls equals 3. And for data, let's do. So what do you think this is going to do? Right, syntax wrong. It's n row and n call. So what I've done is I've declared a 3 by 3 matrix, and I've passed in a 9-element array. So the logarithm of all the elements 1 through 9. And all those values fill up the array.
Base 10 logs?
Sorry?
Those are base 10 logs?
No, log is natural logarithm, so base E. Yeah, if you wanted base 10 log, I think you'd have to do log whatever divided by log 10. And so the data that you pass in just fills up the array. So top to bottom, then left to right. And if you want to do some other array, let's say n is matrix. Let's do, I don't know, 2 to 13. Or I'll do something more interesting. I'll do 2 to 4. N row equals, let's say, 3. And call equals 4. And so we get this. And now if we want to multiply these, we can do m percent times percent, because that's n. And we have matrix products. By the way, did you see how when I declared n, the 2 to 4 matrix got 2 to 4 vector got cycled until it filled up all of n? All right, if you wanted to take eigenvalue decomposition, this is also something we can do very easily. We can do eigen m. And so this is our first encounter with a list. So eigen m is a list with two keys, values, which is this array here, and vectors, which is this array here. So if we wanted to extract, say, this third column from the eigenvectors matrix, because the eigenvectors are column vectors. So we can do vec gets eigen m $ vectors, comma 3. Oh, done. Vec is that, as you might expect. Then say m times % times vec. So the result here certainly looks like if we took the third eigenvalue here, which corresponds to the third eigenvector, and just multiplied everything in this eigenvector component-wise by the eigenvalue. And that's what we would expect, because that's what eigenvalues are. Has anyone here not taken linear algebra? A couple of people, OK. Just turn your brains off for a bit. And indeed, if we take eigen m $ values 3, right, yeah, times vec, we'll get the same thing. Just formatted differently as a row vector instead of a column vector, but big deal. Yeah. And so those are basically nice things that we can do with matrices. We demonstrated lists. I should demonstrate the nice things about functions as well. So let's look at this function. It's called func gets function n squared. Actually, let's not do that. A squared plus b. So one thing about functions, again, is you don't need explicit return statements. You can just, the last statement evaluated will be the statement returned, or the value returned. So in this case, we're only evaluating one statement, a squared plus b. That will be the default return value. It never hurts to put in return values explicitly, especially if you're dealing with a function with very complicated logic flow, but you don't need them. So now we can do func, 5, 1, and this is basically what you'd expect. Something else we could do, we can actually do func b equals 1, a equals 5. So, and if we specify which number here, or which argument goes to which argument in the function, we can flip around these values however we want.
Is there
Yeah?
a reason to write it out with the b equals as opposed to just using the numbers in the comma?
Yeah, usually you do this if you have functions with a lot of arguments that might often be like flags that you'd only want to use in rare occasions. And this way you can refer to the specific arguments that you want to use non-default values for, and you don't have to write out a bunch of flags equals false after them. Or I can write this again with a default value like b equals 2. And then I can do f func, I'll do 4, 1 this time, and 17, which is 4 squared plus 1, as you might expect. But I can also just call this with func 4. And I'll get 18, because I don't specify b. So b gets the default value of 2. OK. So now, if you're following along with the demo, type this line at your command prompt and see what comes up. Actually, don't do that. Type this. You should get something like this. So mtcars is a built-in data set for basically demonstration purposes that comes with in by default with your R distribution. This is a compilation of statistics from a 1974 issue of Motor Trends magazine on a number of different car models. So there's miles per gallon, cylinders, I forget what disp is, horsepower, yeah, and probably. If you just Google MT cars, then one of the first results will be from the official R documentation, and it will explain all of these data fields. So weight is, WT is weight of the car in tons. Cusec is the quarter mile time. So now we can do some fun things about empty cars is a data field, so we can do things like row names, empty cars. And this is just a list of all the rows in the data set which are names of cars. We can do call names, empty cars. This. If you do empty cars, some numerical index, like 2, we'll get the second column out of this, which will be cylinders.
What did you do?
I typed empty cars brackets 2, which gave me the second column out of empty cars. Or if I want a row, I can type empty cars, comma 2, for example. Actually, sorry, other round 2, comma. Like that. And that gets me a row. This here just gives you a column. So, but column as a vector. Oh, sorry. Just realized now I forgot to demonstrate some cool things about vectors that you can do with indices. So let me do that right now. So let's do C gets, putting this on pause, 2 times 1 to 10. So C is just going to be a vector 2 through 20. I can take elements like this, C2. I can pass in a vector like this, C. Let me use a different name than C, like vec C. Basically, I'm doing this so you don't get confused between C as a vector construction function and then C as a variable name. To vec brackets C 4, 5, 7. This will get me out the 4th, 5th, and 7th elements of the array. I can do vec, put in a negative index, like -4. That will get me out this with the 4th element removed. Then if I want to do slices, I can do like vec 2 through 6. 2 colon 6 is just another vector, which is 2, 3, 4, 5, 6. Spits out that. So anyhow, back to empty cars. All right. So let's do some regressions. Let's say model gets, let's linearly regress, I don't know. First let's do attach empty cars, or empty cars, of course, empty cars. So first let's do model LM. Let's regress miles per gallon on tilde. Let's do weight. And then data frame is empty cars. So summary model. OK. So this looks a bit complicated. But basically, saying is if we try to express miles per gallon as a linear function of weight, then we got this line here, which intercept of 37.28. Yeah, 37.28 would be the theoretical miles per gallon of a car that weighs 0. And then for every additional pound, sorry, not for every additional pound, for every additional ton, you knock about 5 miles per gallon off of that. Both of these coefficients, you can see standard errors there, and they're very statistically significant. So like we can be very certain to 1e 10 to the negative 10, so 1 times 10 to the negative 10, that if you make a heavier car, it will have worse miles per gallon. Or we can test some other model, like instead of regressing this on weight, let's regress it on log of weight, because maybe the effective weight on mileage is somehow not linear. This gave us an R squared of 0.7528, so let's try this. I'll assign this to a different variable too, model 2. So summary, model 2. All right, so again, we got our best fit line here. And this time, so this is saying basically that every time you increase the weight of a car by a factor of e, you lose this many miles per gallon. And so this time our residual standard error is, that doesn't matter really. Residual standard error is basically just the standard error that you have left after you take away the trend line. And our R squared here is 0.81, which is a bit better than what we had before, 0.52. And so now let's add a term to this regression. So let's regress miles per gallon both on log of the weights and, I don't know, let's do Q mile, quarter mile time. OK, must have the, what's it called? Right, Q sec. Q sec. Actually, sorry, so let me call this something else besides model 2. Let me call this model 3. And so now we can do summary model 3. And so again, this is basically what you might expect. You have a positive intercept. The effect of increasing weight is negative. And the effect of increasing quarter mile time is positive, but though less so than weight. Now intuitively, you can make sense of this by saying, think about sports cars. These have very fast accelerations, so very short quarter mile times. They're also going to use more gas, whereas more sensible cars are going to have slower acceleration, higher quarter mile times, and use less gas, so higher miles per gallon. Great. And so now let's try to plot something like this. So let's do, so bare bones, we can do plot, because I've attached this data frame before. We can just do plot, WM, WT, MPG. Make this a bit bigger. And how do I make this bigger? Yeah. No. There, we basically have a scatter plot, though the points are kind of hard to see on this. I don't remember offhand what the syntax is for changing the plot, so I guess this would be a good time to bring up. There's a very nice built-in help feature, help, quote, function name will bring up basically anything you'd like. Right. I think I should do this, type equals p for points plot. Did that change anything? No, not really. All right. Huh. Yeah, for some reason when I did this on my own computer a while ago, all the scatter points were much clearer. But Lewis. Anyhow, though, are all these, like, are the scatter points, like, kind of visible? There's like one there, a few there, a few there. There's that. Like, you can sort of see them, right? So if we want to add a best fit line to this plot here, it's just a bit bare bones. Let me make it a bit nicer. Main equals. Versus weight miles per gallon. Again, you can see how useful optional arguments are here, with also not having to put things in a certain order with keyword arguments when you have plots, because these take a lot of arguments. That equals weight, tons. All right. Huh. Okay, yeah, this device is being a bit annoying, but you can see sort of up there, there's a graph title. On the side, over here, there's, on the bottom here, there are access labels. I don't remember offhand what the commands are, what the function arguments are to increase the size of those labels and titles, but they're there. And so if we wanted to add best fit line, we could do something like, I have the syntax written up here. So remember, we just had model was mpg weight empty cars. So if we want to add a best fit line, we can do AB line model, and boom, we have a best fit line. It's kind of hard to see again. I'm quite sorry about the technical difficulties, but it runs basically top left through bottom right. And if the scale were bigger, you could see that the intercept is what you can find from the summary statistics if you typed summary model. OK. So I hope everyone gets something of a sense of what R is, what it's good for. You can make far nicer plots than this on your own time if you'd like. So the foreign function interface. This is something that is not typically covered in introductory lectures or introductory anything for R. It's not likely you're going to need it. However, I've found it useful in my own projects in the past, and there's no good tutorial for it online. So I'm just going to rush you all through this, and then you're free to leave. Basically, the foreign function interface is what you can use to call out to C functions within R. Internally, R is built on C. R's arithmetic is just C's 64-bit floating point arithmetic, which is type double in C. And you might want to do this for a bunch of reasons. For one, R is interpreted. It's not compiled down to machine code. So you can rewrite your inner loops in C and then get the advantages of using R, like it's a bit more convenient than C. It has better graphing facilities and whatnot. And while still being able to get top speed out of the inner loops, which is where you really need it. Reusing existing C libraries is also important. If you have some C library for, like, I don't know, Fourier transforms or some very arcane statistics procedure used in high-energy astrophysics or something, I don't know. High-energy astrophysics isn't even a thing, I think. Then you can do that instead of having to write a native R port of them. And again, like, if you look in most of R's like default libraries, on the internals are going to use the foreign function interface very extensively. They'll have things like Fourier transforms or computing correlation coefficients written in C, and then just have R wrappers around them. The interface is a bit difficult. I think its difficulty is exaggerated in a lot of the instructions you'll find, but nevertheless, it is a bit confusing. And I haven't been able to find a good tutorial for it, so this is it right now. Again, this whole segment is more for later reference. Don't worry about copying everything down right now. So the following instructions are for Unix-like systems, so Linux, BSD, OS X. I don't know how this works on Windows, but please just don't do your final project on Windows. You really don't want to. Unix is much better set up for casual programming. All right. So basically, foreign function interface. If you want to write a C function for use with R, it has to take all of the arguments as pointers. So for single values, this means it's pointed to the value. For arrays, this is a pointer to the first element, which is what array names actually mean. Again, this is something you should have pretty solidly down after preset 5. Array names are just pointers to the first element. The floating point type is double, and your function has to return void. The only way that it can actually tell R what happened is by modifying the memory that R gave to it through the foreign function interface. So I've written this example here. This is a function that computes the dot product of two vectors. It takes two arguments, vec1, vec2, which are the vectors themselves, and then n, which is the length, because again, R has built-in capacity to find out the length of vectors, but C doesn't. In C, vectors is an arbitrarily limited chunk of memory. So the way you can calculate dot products is just set this out parameter to 0, and then just iterate through from 1 to star n, because n's a pointer to the length. Just add something to this out parameter. And it can be good practice if you're going to do this to write two separate C functions. One of them just takes the arguments and the types that they would ordinarily be in C. So it takes array arguments as pointers, but But single value arguments like n, it just takes as values by copy without pointers. And then it doesn't have an explicit out pointer. And then you can have a different, basically, wrapper function that basically handles the requirements of the foreign function interface for you. And the way you call this in R is once you have your function written in C, you type r command schlib, r command shared library, foo.c, or whatever your file name is, in the OS shell, not in the R terminal. And this will create a library called foo.so, and then you can load it in our script or interactively with this command dyn.load. Then there's a function in R called .c. This takes arguments that are first the name of the function in C that you want to call, and then all the parameters to that function. They have to be in the proper order. You have to use these type coercion functions as integer, as double, as character, and as logical. And then what it returns is a list, which is, again, just an associative array of the parameter names and the values after the function has run. So in this case, because .prod in our has arguments vec1, vec2, intent, and out, to .c we have .prod, the name of the function we're calling, vec1, vec2, type coerce, the length of either vector. I just chose vec1 arbitrarily. It would be more robust to say, like, as integer min length vec1, length vec2. And then just as double 0, because we don't really care what goes into the out parameter because we're setting it to 0 anyway. And then result's going to be a big associative array of basically vec1 is whatever, vec2 is whatever. What we're interested in is out, so we can get that out. This is, again, a very toy example of a foreign function interface. But if you have to compute dot products of massive vectors in loops, or if you have to do something else in a loop, and you don't want to rely on R, which does have a bit of overhead built into it, this can be useful. Again, this is not usually an introductory topic to R. It's not very well documented. I'm just including it because I found it useful in the past. So, bad practices. I mentioned that there's a for loop in the function. Generally, you should, in the language, you should generally not use it. Based on how R just implements iteration internally, it can be slow. They just also look ugly. R handles vectors very nicely, so oftentimes you don't need to use it. Then you can usually replace a vector often with these functions called higher order functions, map, reduce, find, or filter. I'll just give some examples of what these do. Map is a higher order function because it takes a function as an argument. So you can give it a function, you can give it an array, and it will apply the function to every element of the array and return the new array. Reduce, basically, you give it an array, you give it a function that takes two arguments. It will apply the function first to the first argument in some starter value, then to that result in the second, then to that result in the third, then to that result in the fourth, and then return when it gets to the end. So for example, if you want to compute the sum of all the elements in an array, then you might call reduce with, and hand reduce, just an addition function, like func AB, return A plus B, and a starter value of 0. And all these are, like, you can find them described in the R documentation in any textbook on functional programming. Then there's also this class of functions called apply functions, which they're a bit hard to explain. But if you look in Schlesi's book that I cited at the beginning, he explains them pretty well in his appendix on R programming. All right. More bad practices. Appending to vectors. Yeah. Other thing I should correct, that in that first line, vec arrow, that arrow should not be there. You can assign to a vector, again, by taking its length plus 1 and assigning some value to that. That will extend the vector, or you can do vec equals c, vec new value. Again, if you use c with one argument as a vector, the resulting hierarchy gets flattened. So you'll just get a vector that's extended by 1. Never do this. The reason why you shouldn't do this is this. When you allocate a vector, it gives it a certain chunk in memory. If you increase that vector's size, it has to reallocate the vector somewhere else. And so reallocation is quite expensive. I won't go into the details of how memory allocators are implemented on the operating system level, but it takes a lot of time to find a new chunk of memory. And also, if you're reallocating lots and lots of progressively larger chunks, well, you end up with something called memory fragmentation, where the available memory is divided into lots of little blocks in the memory allocator's point of view, and it gets harder and harder to find memory for other things. So instead, if you need to do this, if you need to grow a vector from one end to the next, instead of appending to it constantly, you should pre-allocate it vec arrow vector length equals 1,000 or whatever. And then you can just assign to the vector's values one at a time after you've allocated it once. I ran into this again in my summer job when I was writing in R a differential equation solver. Not symbolic, numerical. The idea is that once you have one value for your solution, you use that to compute the next one. So my natural naive inclination was to say, OK, so I'll start off with a vector that's just the initial value, compute from that the next value that goes on to my solution vector, and append that, create something else, append that. It went very, very slowly. And once I realized this, and I changed my system from appending to this vector like 10,000 to 100,000 times to just pre-allocating a vector and just running with that, I actually got more than 1,000-fold speed up. So this is a very common trap for R programming. If you need to build up a vector piece by piece, pre-allocate it. Another common trip up, this is my last slide, don't worry, is error handling. R, to be frank, doesn't really do this very well. There are a lot of problems that can crop up. For example, if you get an array or a vector out of a function that you were expecting a single value to come from, or vice versa, and you pass that into a function that you wrote expecting a single value, that can be a problem. Certain functions return null, as do, say, reading from a non-existent key in a list. But null isn't like C, where if you try to read from a null pointer or write to a null pointer, it just segfaults, and if you're in your debugger, it tells you exactly where you are. Instead, null will do, like, functions will do unpredictable things if they're handed null. Like, if you try to do max null, it'll give you negative infinity. And so, yeah. And so this happened to me once when I had changed a bunch of fields in my list structure once without changing them elsewhere when I was reading from them, and then I got all sorts of random infinity results cropping up, and I had no idea where they came from. And unfortunately, there's no real R strict mode where you can say, if something looks like it might be an error, just stop there so I can be disciplined and fix that. However, there is something called stop if not. This is the equivalent to C's assert. If you've talked about that, I don't think C assert is a lecture topic, but your section leader might have gone over it. And stop if not basically takes any predicate, so any statement that can be true or false. And if it's false, it stops the program. It tells you exactly what line you were on and what condition failed. And this is very useful, for example, sanity checking, function inputs. So if you have a function input and you expect, say, if the user's giving me a date, I want the date to be just a vector of length 1 and somewhere between 1 and 31. And if not, I know something's gone wrong, and I should just stop there before this has random knock-on effects with code that it's harder to trace through. So that's one possible use for stop if not. Anyhow, OK, so that's the end. Thank you so much for coming. I am a rank amateur at this, so sorry if you're bored or confused or what have you. I'm happy to take questions by email at connorharris@college.harvard.edu. This goes also for everyone watching this live or later on. Also, though I'm not a TF, I am also very willing to serve as an unofficial advisor for anyone who's using R in a final project. If you'd like to do that, then just talk to your TF and then write me an email so I know what you're working on, and I can set up meeting times with you if you want. So again, thank you very much. I hope you enjoyed it. Of course.
Just what kind of a project would a CS student use R for?
So if you're not doing something that's purely in data mining, for example, And there are lots of things you could do with that with data mining and machine learning. You might want to use R for a component of something. I brought up originally the example of if you're writing a website and you want to run automated statistical analysis of your server logs at a certain time every day, that might be something that's very easy to do in just a brief R script that you can schedule to run every night, for example. And I'm sure if there's any reason you would want statistics or graphing capabilities and have this run automatically instead of having to interact with things in Excel, for example, that's something you might want to use R for. So any more questions before I leave? No? All right. Well, again, thank you very much for coming.